Hey, this is Mr. Milleman, and I'm back to talk to you about the periodic table. The periodic table is that wonderful table we use to organize all of the known elements. Well, how'd we come up with it? Well, in the 1800s, there were a number of different scientists trying to organize the different elements that we knew about. In the 1860s, we knew about 60 or so elements. And one particular scientist, a Russian scientist named Dmitri Mendeleev, started to become obsessed by putting the periodic table together. I mean, really obsessed. I mean, gotta have hot buttered popcorn at the movies obsessed. He started working on this thing so hard that he was able to put something together. Well, he started with a lot of different things. He started with the density, he looked at melting point, he looked at appearance. Nothing really seemed to fit or make sense. Then he found atomic mass. He started to organize his periodic table based upon atomic mass. And when he did, he saw a fit. This fit was a repeating pattern. So when Mendeleev organized the periodic table by atomic mass, he saw a repeating pattern. He saw that things were coming up periodically, or in a period. But as Mendeleev worked, he found that there were gaps in his periodic table. Some things just didn't quite fit, so he just kept working and kept working. Well, he decided that these gaps were missing or unknown elements. Other scientists just assumed, oh, well, the periodic table doesn't fit. It mostly works, but there are some places where it just doesn't. Well, Mendeleev didn't give up because, like I said, he was obsessed. He wanted to make sure that he had everything. So he started to make predictions on these gaps, these unknown atoms. So as he was coming up with these unknown elements, he was making predictions on their atomic mass, their reactive properties, everything. And guess what? When they'd finally discovered all the gaps, they filled in all the gaps, by 1886, he was right about them all. Now, the more elements that were discovered, the more things didn't quite fit exactly as he planned. And he was starting to wonder, well, why isn't his table working quite the way he thought it would? He'd been obsessed, he'd done the research, he'd made it perfect. But there were a few problems. So he just kept wondering, what's going on? So as time went on, he couldn't figure it out, and other scientists tried to come in and figure it out. In the early 1900s, a fellow named Henry Moseley, he came along and he decided that we're going to start looking at protons, because by this time he had discovered the subatomic particles, the protons. And what he did was he started to organize the periodic table based upon protons, the atomic number, rather than the atomic mass, protons and neutrons added together. So, as he was measuring based upon the atomic number, he reorganized just a few things, and everything fell into place. And the periodic law was born. The periodic law says the repeating chemical physical properties of elements change periodically with the element's atomic numbers. Well, this goes along with those numbers of protons, the atomic number. And all of the newly discovered elements, the ones after Mendeleev made his first table, they fit into the periodic law. So finally, we've got a system that all works. So our periodic table is based on the atomic number, the number of protons in the nucleus of each atom. Scientists started to organize the periodic table into classes: metals, metalloids, and nonmetals. And they used the number of electrons found in the outer shell of the electron ring to help determine where they belonged. Those outer electron shell electrons, well, that's the valence electrons. They used those. They also used the zigzag to help them decide where things should go. As you can see, most of the elements on the periodic table are metals. Well, metals are usually found as solids at room temperature. They're good conductors of electricity, and they usually don't have very many valence electrons. The nonmetals are found to the right of the zigzag. They're mostly gases at room temperature. Most of them have an almost complete outer shell of electrons, and their properties are pretty much the opposite of the metals. The metalloids are found along the zigzag. They have some properties of metals and some properties of nonmetals. They're called semiconductors, and they have about half a full set of electrons in their outer shell. The periodic table is arranged in an almost grid-like pattern. It's got columns and rows. Well, the columns are called groups, and elements within a particular group have similar physical and chemical properties, and sometimes they're called families. The rows are called periods And that's because as you move across the table from left to right, the reactivity and conductivity of the elements changes gradually over time. They fall in periods. So let's take a closer look and see how we can break all of the different groups down. Let's start with the alkali metals. They start with lithium and work their way down. They're extremely reactive because they only have one electron to give away. They're shiny, they are silver, and they're very soft, and they have a low density. The alkaline earth metals are kind of similar to the alkali metals. They are shiny and silver, they're a little more dense, and they're still reactive, but a little less reactive, and that's because they have to give away 2 electrons, which is a little harder than just giving away 1. The transition metals, it's a rather big block, isn't it? It's an awful lot. It's not just one group, it's actually 10 groups, groups 3 through 12 all put together. Well, they're similar to the alkaline earth metals in that they are silver and shiny. Well, some of them are silver, some of them are not. But they're good conductors of electricity and thermal heat. And they're a little less reactive than the alkaline earth metals and anything to their left. The next group is the boron group. Not a very original name. It's group 13. Well, boron is a metalloid, and the rest are all metals. They're kind of reactive, and they're all solids at room temperature. But not much else to tell about this group. Group 14 is the carbon group. Not a very original name, once again. Well, the carbon group is carbon and everybody below it. You'll find 1 nonmetal, 2 metalloids, and 3 metals. Well, each of these have 4 electrons in their outer shell, so reactivity is a little inconsistent here and usually depends on the particular element involved. Also, they're all solid at room temperature. Group 15 is the nitrogen group. Once again, not a very unique name. Well, in the nitrogen group, you'll find 2 metals, 2 metalloids, and 2 nonmetals. Each one of these elements has 5 electrons in its outer shell, so reactivity really varies, so much so that nitrogen is not very reactive at all, but phosphorus is very reactive. And you'll also find that every one of these elements is solid at room temperature, except for nitrogen. Group 16 is the oxygen group. Once again, you get the picture. Well, here you'll find 3 nonmetals, 1 metalloid, and 1 metal. They're all going to be solid at room temperature except for oxygen, and since they all have 6 electrons in their outer ring, these valence electrons make them pretty reactive because all they need to do is to add 2 more electrons in order to get that full outer shell. Group 17 is the halogens. They're all nonmetals, and they all have 7 electrons in their outer shell, and these 7 valence electrons lead to them being extremely reactive, especially with the alkali metals. When they form with the alkali metals, they form a violent reaction. They're not very good conductors of electricity, and you'll never find them in an uncombined form in nature. Group 18 is the noble gases, and like their name, they're all gas. These noble gases have full outer shells, so they have no valence electrons to give or to take. Since they're full, they don't react under normal circumstances. These noble gases are called such because if you go back in time, about 1,000 years, you'll find that throughout Europe, you'll find noble people. These were the rich landowners of Europe, and they had a lot of servants who worked for them. Well, they were noble, so they couldn't mix with the regular people, the workers. So they were noble. They were too good to mix with the others. Well, just like our noble gases, they're too good to mix with anybody else, so they're unreactive, and so they don't mix with the others. They're found over on the far right side of the periodic table. Hydrogen's really kind of a deal all its own. It's very unusual, and that's why it sits way up above the alkali metals as opposed to being part of the group. We put it there because that's kind of the best place for it to fit, because like the alkalis, it has 1 electron to give. Well, it doesn't really fit with the alkalis because it's a gas, and it really has properties more similar to that way over on the other side of the halogens. Like the halogens, it also has 1 to get. So if it can get or give 1, which makes it pretty reactive. Well, it's got the physical properties of the halogens, so it kind of fits over there as well. So we're really not sure where to put it. It's a colorless, odorless element And 90% of the universe is made up of hydrogen, so it's all around us. But it doesn't really have a place to go, so we kind of put it off by itself. The lanthanides and the actinides are found at the bottom of the table. And they're really just transition metals that we don't have a better place for. It just makes the table narrower. And the truth is, it just fits on a piece of paper better. And that's the only reason that they're there. Because if we don't, it's going to be a really wide table. The lanthanides follow lanthanum, which is number 57 on the periodic table. And the actinides follow actinium. And once again, it's just to keep it narrower. Because if you don't, your periodic table is going to end up looking kind of like this.